All right, it is 6 o'clock. So welcome everyone to the January 2025 Seattle Rust User Group Meetup. I hope everybody had a great holiday, and I guess we're back at it now. So I'd like to welcome everyone, and also remind folks that we operate here under two codes of conduct. One is by our hosts, Microsoft, for giving us this facility, and the other is the Rust Code of Conduct. The bottom line is, it boils down to treat each other with decency and respect. If you feel that someone is not treating you well, please let them know. And if the situation persists, please let me know, and I will step in to assist. The slides that I'm going through right now, you can always find them at slides.com/U007D, which is my online handle, alias, whatever, that you'll find on in technical forums. Hi, yeah, this is a Rust meetup. You're welcome to join if that's what you're looking for. All right. Great. It's like, oh no. All right, I'd like to begin with some introductions. How many here have not attended a Rust meetup before? Or this Rust meetup before? Okay, we've got 1, 2. Okay, so we got a couple of folks. We're a very friendly bunch. It's important that this is a place that everybody feels at home. So we want it to be a little bit less of a lecture, more of a dialogue back and forth. Whenever we've asked, about 60% of the room would put up their hand if we asked if they consider themselves to be a Rust beginner. So if you're a beginner in Rust, even if you may or may not be a beginner in programming in general, you're quite welcome here. And if you're intermediate or advanced in Rust, we also have folks who fit that category as well. So welcome aboard. My name is Brad. You'll see me online as U007D, or if you want to pronounce it, Curly is, I guess, the correct pronunciation of that. I've given my intro a number of times, but ultimately I started back when the dinosaurs were still roaming around in the 80s on a Commodore 64, learned to program in BASIC at first, and then had to pretty much delve into assembly language after that because of the Commodore BASIC version 2 that was packaged with that particular computer, which turned out to be a blessing in disguise. So I've didn't know it at the time, but I've been pretty much loving low-level programming ever since. And those are some of the languages that I've dabbled in, working on building an electric car. So seeing if I can make that happen from scratch. Anyone else want to share a little bit about themselves? Don't be shy. It's okay. I'll actually grab a microphone. Anyone? How about you, Carl? I know you're not shy. Okay.
So I've been programming since high school in BASIC and Forth. I was at Microsoft for 25 years, mostly in the research division as a research programmer. Right now I'm a volunteer on open source projects having to do with genomics, Python, and Rust. I started Rust 5 years ago on a genomics project that had a C++ extension and was driving me crazy, and I switched to be a Rust extension. And now I'm very happy. And I went to college for a long time. Part of that's because I just enjoy programming in general and other topics like probability, which we'll talk about a little bit in a bit.
Great, thanks. Would anyone else like to say hi? We have a shy group tonight. Just introducing yourself. Maybe talk a little bit about your interest in programming or what brings you to the world of Rust. If I could flip that on for you. There you go.
Microphone. Fancy. I wouldn't usually mention this, but you got the shirt. I was born in the Netherlands. Been programming since, I don't know, since I was little. I guess my interest in Rust is I like static languages because you can change things and the compiler will tell you things break. I've been using it for some hobby projects, and right now I'm working for a company called Lynx. They make a real-time operating system, and I'm working on having Rust compiler support for that operating system. And the compiler pretty much just works. The standard library is another story. Oh, and I'm called Tim. Did I miss anything?
All right. Anybody else like to introduce themselves? Great.
Hi, I'm Michael Leggett. As my son Owen, we're actually mostly here for him. I'll let him put him on the spot and make it really awkward for him. He's been programming for a long time, and I've been doing it for not from as young age, but for a while. But yeah, why are we here to learn about Rust? What do you love about Rust?
I think, well, I started learning Rust a year ago because someone at my school was using it for like I think quadratic equations or something. And I like it because earlier today I spent like, I don't know, 5 hours coding something, and it just worked the first time I ran it. So
Thank you. Yeah, a lot of people say that they're really shocked because in Rust, if it compiles, it generally works. And obviously, it's not 100% true, but more so than most other languages. And it's kind of shocking when you see that happening. Okay, great. Thank you for those introductions. It's nice to get to know one another. So I wanted to make people aware of the upcoming meetups. We usually meet the third Thursday of every month. Typically, that doesn't happen in the last 2 months of the year just because of Thanksgiving and Christmas holidays. But for the rest of the year, unless there's an event in this space, we'll try to meet on the third Thursday of each month. I'd like to put out a call for volunteers. People say, oh, get a little lower in their chairs. I try to run this group very sustainably. Right now, I'm the only person running the group. And so it doesn't take a ton of time. And that's important to me because otherwise, if it's not sustainable, it doesn't happen on a regular basis. So I've got some ideas here for working with some folks to have some small jobs, each of which would amount to less than 1 hour a month, probably less than 30 minutes per month. But one is organizing the speakers in the Discord channel, not Signal, but Discord. In the Discord channel for our group, what I can, what I have put together is an area for the talks that are coming up. And for each month, I have a simple posting, which I go back and can edit and to say who's talking and what audience the talk is for and how many minutes is in the talk. So when somebody reaches out to me on Discord and says, hey, I'd like to give a talk, I'm like, great, give me, who do you want to be introduced as? I use first name and last initial. What level is your talk aimed at? Title for your talk, and how many minutes you'd like. And you pop it in here. And once you get to about 90 minutes or so, that day is probably going to be full. And then you just move to the next month where you do the same thing. So each month, either I or you could stand up here and ask for speakers, which you'll see in a slide coming up. But that's really the extent of the commitment for organizing speakers. Okay. Posting videos. So some of you know and have asked me. I tried my best to get a bunch of videos posted to the YouTube channel over the holidays, but I have not yet posted October, November, and December. I tried actually this week to do that, and it turns out that either I've lost a few brain cells or Open Broadcast Studio has changed the UI. But I thought I used Open Broadcast Studio to just chop the ends off the recordings that I get from Microsoft. and then I upload the whole thing up to YouTube. And I can't remember how I did it. So maybe it's a little bit of both. I'm not sure. So I'll spend a few more minutes on that. But generally speaking, I don't do a lot of production work. I just trim the beginning and end so that it's appropriate for the meeting. I don't do chapter markings or anything like that and just push them up. We get about 50 views, right, on the videos. So that's something that someone could do. And again, that would be certainly less than an hour a month. And finally, updating the Meetup and Discord schedules. In Discord, depending on your user interface, there's a little calendar. And this calendar talks about all the upcoming events. We have this place booked at these dates up through June. And then on meetup.com, I have just, if I go here, because it makes it a little easier if people can see the upcoming meetings. I've just set up I just want to see the group. Here it is. I've set up the group, and you can see here it has upcoming events. So there's the one that's going on right now, plus February, March, April, and so on. And I've just plugged in a little template. And that template, if you go into edit the event, it's already got all the information here about when the meeting is. And then this is a matter of plugging in the speaker data that I just showed you in Discord for that particular month. So this one would be maybe 10 minutes. So any thoughts? Anybody at least notionally interested in any of those? Yeah? Okay, thanks, Carl. Yeah. What did you're thinking you might be able to help on one of the... Yeah, okay, thank you. Oh, thank you, appreciate that very much. Yeah. Okay, thank you guys, appreciate it. All right, so what I'll ask each of you to do, could you reach out to me on Discord? And then we'll just divvy up the tasks, and that's great. If you're finding it's taken too long or whatever, let me know, and we'll fix it. Because I mean that it should be well under an hour a month. Got to keep it lightweight. Thank you guys, appreciate that. All right. So each month, we like to get together outside the front doors. And as the weather gets cold, we tough it out. But often we meet down at Flat Stick Pub. We have some members who are not quite old enough to drink. You might have even heard from one tonight. So we've been thinking about how can we find a place to meet where everyone can be included. And so we've all actually had several email exchanges, and we can't find a place, and that place doesn't look good or big enough. And we've been beating our heads against the wall. And just through complete coincidence, been talking with Lloyd, who's here. Hi, Lloyd. And we're going to have a sort of a cross-language panel talk at some point in the future. And Lloyd said, why don't we get together and discuss this? We all, and the Northwest C++ Club, Northwest CPP Club, we all get together at Red Robin after. And I'm like, why didn't we think of that? So I have no idea how big or how small like the Redmond Red Robin is, and whether or not a group sort of maybe this size or half this size would overflow it. But I'm going actually tonight. I won't be joining the Rust group at Flat Stick Pub tonight, but I will be going with Lloyd and the CPP Club to talk about the panel and other things that we might want to do in the future as sort of cross-group collaboration. What would be great is if that place had enough space and we could bring anyone who wanted to go. So if you guys have ideas about places that would work like a Red Robin and would have enough space, typically we get maybe half of the group wants to sort of go afterward. So between 10 and 15 people, please let us know, because we are looking for a good place so we can include everyone. Great, thank you. Okay, so you'll be able to find the meetings on YouTube, posted on YouTube shortly afterward. Typically, Microsoft will provide us with a link or a download to the meeting recording, within a week after the meeting, and then we can post it. As always, there's a call for speakers. You saw that I have both tonight and February pretty much ready to go. So if you are thinking about something that you'd like to talk about, we'd love to have you come up and speak for the March meeting. Does anyone have any topics in mind that they might want to talk about? Okay. So if we have time permitting tonight, I'm going to talk about lifetimes in Rust, right? The bane of beginners, right? Lifetime. But I'm going to do it in a way where you do not need to be an expert. I did this talk once before, and it was actually very interactive. People loved it. So I want to encourage everybody in the room to think about this as a way of giving a talk, is actually you receiving a talk. If there's an area of Rust that you're interested in, and maybe you don't know enough about it, you could find a video on YouTube, typically 15, max 15 to 20 minutes long, and you could stand up and present the video. Not as a domain expert where you're the one getting questioned, but you're flipping the script and you're saying, this is something I'm really passionate about. And then you play the video and you stop it at places where you have questions. And then you're speaking with the audience and people, you got a whole room full of people focused on things that you're interested in. It is a fantastic way to grow and learn. And the conversation ends up being very interactive. It's not like, oh my gosh, I have to be up front and, be in front of everybody and do public speaking. So it doesn't really matter your level of Rust. It's what really matters is your level of interest. And if you have an interest in something, please reach out to me and I will help you find a presentation format that you're comfortable with. And the group will benefit from hearing about something that they might not otherwise know about. Okay. Any thoughts or questions about that? So if any of you are working on hobby projects, I'm talking, I'm building an electric car. Yeah, there's stuff I could be bringing in and showing, and I got to get around to that and so on. But that's the kind of thing that if you're working on even like a small project, it doesn't have to be something huge. You can bring it in and show us how it works. Okay. So we'll keep chatting about that. Okay, so tonight we have 2 talks. First one is with Peter, and the topic is coding with AI help. And that's interesting because Is this February? Do I have the wrong dates? Well, let me check. Let me check my my scheduled talks here. January. Ha! I got the wrong one. Sorry, everybody. Good. That's right. That's right. This is my cry for help. Exactly. Thank you. Yeah, this is very interesting. All right. So instead of that's February's set of topics. Because I know I saw Sandeep, and you even asked me, Sandeep, if I had you on the schedule tonight, and I was like, yeah, you're on the schedule tonight. And then of course I had copied February into the slides. Okay. So let's go with this for now. Yeah, because I didn't even see my name on there, and I just said that I was, time permitting, I'd be giving you a talk. Anyway, fixed. As I was saying, Carl will be giving a talk tonight about 9 rules of porting Rust, 9 rules for porting Rust to the browser. It's an intermediate level talk for about 30 minutes. Then we'll be hearing from Sandeep. Sandeep has written a book on Rust. Sandeep has written the book on Rust, not the book, but a book on Rust. And he'll be giving us a talk from that book, I guess, Rust Under the Hood. And then if there's time permitting, I'll be doing that video-oriented presentation based on understanding Rust lifetimes. Okay, so does anybody have any items they want to announce before we get started? Anything to do with the Rust community or interesting projects or Rust related or programming related get-togethers that you want to make folks aware of? Nope. Quiet group tonight. Okay. These are going to be wrong. So I'm just going to go to here. All right. Yes. And I'll stop sharing my screen. Mm-hmm. I don't want to. Perfect. All right. You want a wireless mic or a handheld?
Do you really want me to have my microphone on? Did you just tell me to leave it on?
Testing.
Good. Okay. Okay. Welcome. Today I'm going to talk about 9 rules for porting Rust to the browser. The idea is you already have a running Rust program and you'd like it to run in the browser, and we'll see some nice things about that in a second. I got started on this because I have a crate called range set blaze, and I got a user request that somebody wanted to use it inside something that ran in the browser. So I did the port, took some notes, and now can offer advice. Here's an interactive section. If you click the QR code with your phone, you can run my Rust code in the browser of your phone. So try to do this myself. Oh, that's not going to work. Well, you can do it. This is a web app that finds the race results for your running club. So you have friends in your running club, there's some results from a local race, and you want to see if any of your friends are in those results. If you have a friend named Bob Smith, and there's a Bob Smith in the results, it may or may not be your friend. But if you have a friend with a more distinctive name, my last name is distinctive, Katie, and you find it there, then it probably is your friend, Carl. Here's an example. Colleen, that match is worth about 6 points. D is worth 11 points. Her last name is worth 15, but the result has the runner living in Denver. Colleen's actually from Boulder, so you lose a few points for that. So this is all based on an engine that uses naive Bayes. All these numbers are in log odds space. It's all got some probability theory behind it. What's nice is by running this in the browser, hopefully on your own phone now, I'm running it, but you're paying for all the compute. And it's running on your phone, your laptop, your tablet, all that works out super easy. To run this, you have to send the program a list of your friends and where they live. This is all running in your browser. It never comes back to anybody else. So we bypass all privacy issues. And from the point of view of the hosting computer, this is all just static web page and static JavaScript and some other files. So GitHub is hosting this for free, and I didn't even have to ask them for permission. So this is all material from an article that you can find on medium.com. It's also about 1/3 of the material I gave at a workshop at the Rust conference in September in Montreal. Several people in the meetup have heard parts of this, so thanks to Chris, Connor, Ike, Jack, John, Priyanka, and Sandeep. The people in bold have already heard this part of it, so a special thanks to them because they're going to have to hear it again. I already gave you the introduction to me before. Couple things before we start the 9 rules. I'm going to go over some definitions. So if I say native, I mean your main desktop operating system like Linux, Windows, or Mac OS. We'll talk about the standard library, STUD. That's the thing that provides Rust core functionality, and you're probably familiar with string and vector. It's also what lets us do networking and file I/O and find out about the time. We're going to talk about WASM, which is short for WebAssembly. It's the thing that we can compile to instead of your native OS that'll let your code run in the browser. And some other places beyond the browser. If we talk about WASI, I think of that as an extension to WASM for running your code out of the browser that lets your code have some extra capabilities like file access and in the future, not too long from now, networking and better handling of time. Because we're running in the browser, we don't actually have these WASI features, but I'll still be mentioning them incidentally. Okay, we're going to go over the 9 rules one by one. Now I'm just going to kind of give you an overview of what they are. And the first thing is to make sure you have a running Rust program at all, like running on your native system, maybe running on WASM WASI. Also, sadly, the HTML stuff is going to have to be done in JavaScript. So you're going to have be able to do at least enough JavaScript to create kind of a minimal program. Then you'll install some tools. We'll talk about those. You'll compile your project to a library in a little bit different flavor of library than we usually do. You'll find out your program doesn't work because there's some limitations on what types you can use, and we'll learn what those are. You'll change your program to use just those types. Your program will work if you can run your tests. We'll adapt your tests so you can run them. Then you get everything set up, except you're going to have to make some of your dependencies compatible with what is available with this WASM JavaScript environment you're running in. Finally, you can connect the web page and have JavaScript functions calling parts of your Rust functions. And when we're all done, we'll put this all into continuous integration so it doesn't break down the road. So number 1, I'm assuming you have like an executable program and you want to just be sure it can run on your machine. You might also want to check to see whether you can run your tests on WASM WASI, which usually isn't that hard. And if you do these 3 steps, you can see if it runs. If it doesn't run, it's often because of problems like you were assuming a 64-bit machine and the WASM world is 32-bit. There might be some other things going on. You can read yet another article for some tips on that, or you can just skip that for now and hope that things work out as we move forward. What's the simplest JavaScript program that we can write that would kind of give us a framework that we can later add Rust to? So how about one that says line counter, and you click choose file, and you pick a file, and it loads the file, and it tells you how many lines of text are in it. And here's the full HTML JavaScript script for doing that. I'm just going to talk about the parts that are indicated here. There's a thing where the user, you'll get an event in JavaScript with a file or files. You'll take the first files, and you'll see if that's a null or not. If it's null, then the user didn't pick any files, and you'll want to do something to your output on the HTML page. If there is a file, then you want to create what's called a file reader, and then you do some setup, and then you tell the file reader to do read as text. And that says you want JavaScript to read the file as text. That'll be done asynchronously. When it finishes running, it'll call the code in the green box, and this is just JavaScript code for getting the result from the event that said it was done reading, splitting it on new lines, counting them, and then changing the HTML. So if you want, you can find this. You can use this code as your minimal JavaScript, and you can use. If you're using VS Code, it's very easy to interactively create this kind of page and just see the changes immediately on the side. Or there are also Rust local web servers that you can download. The article has some pointers to those. Okay, now we need to install some tools. So the first thing we're going to do is install rust up, we'll say rust up target WASM32 unknown unknown. So that's telling the Rust compiler that we want to be able to compile to a new computer type called WASM32 unknown unknown. The unknown unknown part means that it doesn't have any special capabilities, and that's the flavor of WASM we need if we want to run in people's browsers. We'll also need some tools, which we can install with cargo install. So WASMpack, among other things, has the ability to package up a program and make it, set it up in a format that's usable by JavaScript. And WASM bindgen CLI defines the interface so that to the degree that it's possible, JavaScript can call Rust, can talk to Rust, and Rust can talk to JavaScript. Finally, and most importantly, and most vaguely, it's really good if you install Chrome for testing and Chrome driver. And it's hard. The reason you want to install this special version of Chrome is so that you can run your tests. And the reason you want to do that is because writing for the browser breaks the rule that if it compiles, it runs. And when you're writing for the browser, it'll compile, and then it'll start running, and then it will fail because there's some capability like opening a local file that you're not allowed to do, and the compiler didn't tell you. You only found out when you tried to run it. So you really want to do this testing, but it's kind of complicated. I've got it down to like 8 lines in Linux. I don't really expect you to read them there, but you can look at the article and hopefully get Chrome for testing and Chrome driver set up, which will let you do testing. Okay, so now we have our, now we want to change our program to make it in a form that's suitable so that JavaScript can call it. We need it to be a library. So the first thing we'll do is we'll rename, if we had a main.rs, we'll change it to lib.rs, and then we'll go into our cargo.toml, and we'll say, we'll put a lib section in. Something different than we used to do. We also have to give a crate type, because along with creating the usual Rust library type, which is rlib, we also want to create a C-compatible dynamic library type when we build it. Then you need to add a couple dependencies. WASM bindgen is the thing that lets you different types talk to each other across JavaScript and Rust, and WASM bindgen test is the thing that will let you run tests. Now we're going to create what's probably a new file. It was, I guess I'd seen it before, but I hadn't done it a lot. There's a .cargo config.toml file that's very easy to confuse with the cargo.toml that we always, that we're all very familiar with. It's a different file. It's a file that lets you tell cargo how you want to test. In this case, it's telling you that if you're running a WASM32 test, that you want it to run this program to run the tests. So it just makes things more convenient to set that up. We're going to have to change the code a little bit. Any function that you think you want to make accessible to JavaScript, you should decorate with the WASM bindgen attribute. So I'm changing projects here. This is a function called good Turing that does some kind of statistical analysis on the text of a file. The current version of it, the first version of it, takes a file name, reads the file in by turning it into a buff reader, and if just some more processing not shown here. If everything works, it'll return 2 numbers, and if there's a problem, it'll return an IO error. So for now, we'll just mark that as we want it. We'll have to put a use statement up at the top to include the WASM bindgen types. And then if we have any test code, we'll also include this use statement you see down at the bottom to give us access to the right methods in the test code. And there's also a macro that configures the tests to literally run inside the browser. So we do all this, and it doesn't work. And the reason it doesn't work, well, there are a couple of reasons. First, we were returning, when things worked well in our happy path, we were returning a tuple, a pair of 2 numbers. JavaScript doesn't like tuples. They're not allowed. And if things don't go well, we're returning an error object of type IO error, it doesn't know what that is, and it doesn't allow that either. Okay, we'll see in a slide or two how to fix that. Even after we fix it and run it, it's still going to fail. And that's because the first thing we were doing was trying to load a file from our local disk. And you, for security reasons, you're not allowed to put code in someone else's browser that reads files from their local disk. Not unreasonable. So let's talk about, we said we're not allowed to use tuples and that error thing was bad. What types are we allowed to use? So we're allowed to use all the kind of simple, we call them the copy types, the numeric types, the integers, floats, bool. You can use U64 and I64, the 64-bit integers. But on the JavaScript side, you have to use a special library, but they're still available. You'll notice the 128-bit integers aren't available. And we'll see that again on the next slide. Thank goodness we can use vector and string, because honestly, if you can do vector and string, you can like do anything, right? There is a problem with that. JavaScript, say, wants to pass a string to your Rust function. The way Java represents a string and the way Rust represents a string, they're not just different kind of in who controls the memory. The actual format is different. JavaScript keeps things in 16-bit Unicode, and Rust is 8-bit, but if you ask for a single character, it turns it to 4 bits. It's more modern, but anyway, they're different. It's going to copy it. Likewise, if you give it a vector of bytes, where they are the same format, it's still going to copy it. You can pass a slice of a string or a slice of bytes. That works fine, but it'll still copy it when from Rust to JavaScript, JavaScript to Rust. You can think, okay, maybe I can avoid all this copying by passing it a mutable slice of bytes, because then I'm like telling Rust, just trust JavaScript, and you don't have to control this memory. It will copy it, let you mutate it, and then when it goes back to JavaScript, it'll copy it yet again. So that's what, 3 copies all together. So things work, but there's going to be some inefficiencies in this process. A very nice thing is that we can use a couple of our favorite Rust types, option and result. And especially, now of course, on the Rust side, there are wonderful things that stop us from making mistakes. Because we want the JavaScript to be written idiomatically, on the JavaScript side, they'll be very prone to errors. So an option none on the Rust side will get turned into just a nil on the JavaScript side, and a sum of 4 on the Rust side will just be turned into 4 on the JavaScript side. But you know, you're programming in JavaScript. It's what you expect. You can even send results back, and should, from Rust to JavaScript. On the JavaScript side, if it's the happy path, then you'll just get the happy result. If it's the bad path, it'll throw an exception with your error type, but your error type is restricted. I recommend you just make it a string. But still, you know, it's JavaScript, try, catch, all that works the way you would expect it to on the JavaScript side. The thing that surprised me maybe the most is that Rust structs can be passed over to JavaScript, and you can manipulate them in JavaScript as long as you mark the methods that you want to manipulate them with that bindgen attribute. Not as nice is in Rust, we love our enums as much as our structs. They're not supported if they include any data. They can only be simple enums with, you know, fixed number of variants. So a C compatible enum equivalent to an integer. JavaScript also has kind of a type that can represent anything, which on the Rust side we call JS value. And you can query it. Are you a string? Are you a floating point number? Are you an integer? If you are, tell me what your string value is. And Rust can do all that, and can even create one and pass it to JavaScript if it wants. This is the yep list. Here's the nopes. You can't pass these simple types by reference, but who cares? Because if it's only a short number, you can just pass the number. You can't output a slice of strings or bytes. And the reason is because now we'd have 2 different things owning the memory and controlling it. So that's just not allowed. You can't you can't pass a string with a mutated, and then have the caller get it back, but you can pass a non-mutatable string, do whatever you want to it, and then just pass it as the back as the result. So you can get around any problems. No 128-bit integers. You can't have fixed length arrays, and you can't have tuples, but we already saw you can have vectors. So that's a fine workaround. Both JavaScript and Rust have maps and sets, very handy data structures, but there's no conversion done for you, so there's no easy way to use those across the calling boundary. 2, 3, I guess, types that you can use but you should not use are usize and isize, and that's because you probably think they're 64-bit, but on the JavaScript side, running in WASM, they're going to be 32-bit, so you're just going to cause confusion. Likewise, the character type in Rust is a 4-bit thing, but only some values are allowed. JavaScript will just turn that into a string that just happens to have a length of 1, and it's not checking anything in particular. I think you'd do better just to use a string, and things would be safer. Okay, so now we're going to make 2 changes to the good Turing function we had before. First, instead of passing in the name of a file and trying to open it, we're going to pass in a buffer reader where presumably the file's already been opened. And everything else we're going to leave the same. So this is still a perfectly good function for our Rust code that might want to use it to use. You just have to open the file now before you call it. I didn't want to make any other changes to make it nice with JavaScript because I still wanted to have a nice Rust function. So to create a function that JavaScript is happier with, I'm going to create a wrapper function called goodTuring byte slice, where we pass in a slice of bytes. And now instead of returning a tuple and an error message, we return a vector of numbers and a string if there's an error. When we get this byte array, we turn that byte array into a buffer reader. Then we call our preferred function, the one above. We'll get a result back. If the result's on the happy path, we turn the pair of numbers into a vector of numbers. If it's on the sad path, we turn the IO error into a string with the same message that we would see in the debugger and send that back. One thing I want to point out is both these functions are perfectly good Rust functions, and both can be called from anywhere else in your Rust code. Which means we can create tests. So first of all, our regular test is we only have to make a small change in the test we presumably had before to check some answer. Still works. For the new function, test good Turing byte slice, we'll still decorate it with pound test because it's still a perfectly good Rust function that we can test when we run our tests natively. But it can also be a WASM bindgen test, which will actually run in the browser. And we can call the function and see that it gets the numbers we expect. And I don't think, if you look at the documentation for this WASM stuff in Rust, I hadn't seen other people noticing that the same function could be a test in both frameworks. Before I noticed this and got it working, I would duplicate all my tests, which is a terrible thing to do. And this is much, much better. When you run this, you might have some problems. For example, if you're using a random number generator, the WASM isn't going to like that, but there's a crate you can use called getRandom that'll just make it work. If you're using some time functions, those won't work, but there's a crate called WebTime that might just work. These are the only ones I've needed so far. There are other ones that seem popular. There's one called Request, where your Rust can actually make HTTP network requests. And it does that by calling back through WASM, which then calls back through your browser, which makes the call. I don't know how well that works. There's something called plotters, that obviously does plotting, but also seems to have the ability to control the canvas on the HTML, which means you might have more than just passing numbers and text, which is all I'm doing. And there's something called Glue, which is a toolkit that tries to make as much of the JavaScript capabilities as possible accessible inside Rust. I wasn't that interested in that because it was more for me getting the Rust accessible to JavaScript. When you do all this, you can run cargo test and run cargo test with the target of WASM 32 unknown unknown and see that your code is working. Okay, so now we want to connect our web page and actually have it call these functions in our Rust package. And we can use the WASM pack tool to do that, and it'll create some files that the page will look at. Now, then we'll update our web page, say index.html, and our goal is to have it calling good Turing byte slice, pass in some bytes, and handle errors. And let me just talk about some of the changes we need to make. So at the top, you'll see we need to import both an init function and our function good Turing byte slice, and the location, it was put there by that packaging thing we saw just a second ago. Number two, as often as we want, but before we call the function we care about, we need to call init asynchronously. And it's okay to call it multiple times. It'll only do the init the first time. Before we set up in JavaScript a reader thing and it said read as text, now we want to set up a reader, but for this application, I want to read as a array buffer. And that's in JavaScript. That's after we did a bunch of setup. Then inside that onload await, we get the bytes from after the user has selected a file, and there's only one file. And then we call the Rust function with the bytes. We'll get the two numbers out as a vector, and we'll output the appropriate HTML. But all this was also in a try-catch. So if there was an error, we'll catch the error, and we'll put out the appropriate code there. And you can actually test this. And I can't because I turned off my cursor. So if you test this and select a file, it'll try to guess how many unique words are on the even lines of the text file you gave it, but it's only going to look at how many words were on the odd numbered lines. This is something that Alan Turing and I.J. Good were working as part of their decryption work during World War II. Okay, we're close to the end. I've got a saying, if it's not in continuous integration, it doesn't exist. So if you've ported your code over and got it running and you're very happy, and then you forget about this and you keep working on your library and do other things, this JavaScript compatibility stuff will invariably break. So it's important that whatever continuous integration you're using, like GitHub Actions is the one I use, has tests in, so that every time you make a change in the future to your Rust program, it'll check to make sure your JavaScript, your WASM tests still run. And that's not hard. There's too much to show here, so you have to look at the article. Okay, so last slide. Just in reflection, what's bad and then what's good. The bad part is testing is kind of annoying, and I'm sure a lot of people don't do it. Even though they should. And it's because Chrome for testing is hard to install and hard to manage because it's kind of incompatible with your normal Chrome. Another thing that's bad is we love if it compiles, it works. And now that's not true because they wanted to make WASM as easy to use as possible. They pretended it had the full standard library. And in places where it doesn't, you won't know until you try to use it and it fails. It's nice that it can pass strings and vectors. It's too bad that it's always making 2 copies at least of your memory. It'd be fun if there was a way you could like just pass a slice of memory and not have to make a copy. The good. This is fun. You can take a Rust program like my calculator for running results and just put it on the web and host it for free. And even though I had like colors and things on that little JavaScript thing, I don't know how to program JavaScript. For these kind of superficial JavaScript things, UI things that you need to do, the AI agents are really good at helping you learn that much JavaScript, because it's not a lot. And as we saw, you can run not your regular tests. Even the code that you made to make especially compatible for JavaScript, you can run it both natively and you can run it as a test in the browser on your desktop when you're testing. And the good, I said it was bad that it compiles, it works, doesn't work, but it's nice that you can use most of the standard library. If we move on to embedded, which was the last third of the workshop I gave, then you have to go out and strip all the stuff from the standard library away, and that made things much harder. So this makes things easy. And yet another QR code, and this one's to the article. Okay, thank you. And any questions? Yeah. I don't know for sure. I think if it's a CPU intensive thing in Rust, it's only going to be single threaded. It'll be in their browser, but it's still going to be, I mean, people think WASM is pretty performant. Of course, copying the complete works of Shakespeare, which is what I'm doing here, as a string, that's not efficient. But the CPU stuff maybe is acceptable. And you see people doing in-body simulations and things in WASM. I don't know if they're doing it in Rust. Oh, sorry. The question was, how much performance would you expect to lose by running your Rust in WASM? And yeah.
Add a little bit to that you actually get surprisingly good performance, but the main hits to your performance in WASM are going to be obviously excessive copying from across the Rust WASM boundary, but also whenever WASM needs to interact with the UI, generally it's going to go through the DOM, and so you lose a lot of speed there. There is work in the industry to either flip that or remove that dependency to let WASM achieve its full potential. But if WASM has to talk to the UI, or if WASM has to talk to Rust, certainly the UI is going to be can be inefficient. But if you're careful with your data types talking to Rust, you'll have to get around the issues that Carl pointed out. But otherwise it's surprisingly good performance.
Okay, thank you.
By show of hands, we have our next talk. You know what? Are you ready, Sandeep? Okay, so let's just go straight into our next talk. If anybody needs a drink or a break, please grab it really quickly. But in the interest of time, I think we'll try to get started right away. All right. You need to join the browser and the Teams. I'll show you how. So I will allow my screen. Okay. So the easiest way is to just go to that URL, and it'll come up in your browser. So it's aka.ms/rust -1/16/16. One slash between them, not a dot. It's going to be aka.ms. Okay, and then /rust-1/16. There you go. Okay, so you can join here. Gonna open. You want to mute your microphone on your. Looks like your microphone's muted, so you're good. You can turn down your audio as well.
Audio is off.
Audio is off. Okay, I was wondering.
Oh, is it off?
It looks like it's not quite. There you go. And then join. All right. Okay, so now if you click share, you should be able to share your screen.
I can just share that entire.
Yep, that's fine. And then now you can just go to wherever you want to show, and that's what folks will see. Yep. You can minimize that if you want. Perfect. And you can see here the recording actually won't include the meeting Chrome. So this is what gets recorded. Do you still have your mic? Oh, great. Thank you. Where did you put it down? Right by your glasses. Right there. Okay. Great. Say again?
Should I move there?
Yeah. That way people can, because the camera will be able to see you better. Perfect. Do you want to use this kind of mic or would you like a handheld mic?
Maybe this is.
Okay. And there's the way to turn it on is that little switch right there. I'll leave these right here.
Good evening, everybody. Can you guys hear me? Okay. Okay, so my wife and I have written a book. It's called Rust Under the Hood. You guys can have a look at it. I'm just going to leave it here for some time. Okay. So it was about 6 months ago. So this presentation is not what the book does is it goes into like even assembly level and goes deep and shows like what happens in Rust, and surprisingly large number of things happen in Rust at assembly level, which we are kind of hidden from. So we're going to go through some of them here. Okay, and you can pick up this QR code that will take you to this website where you can find a link to the book. Okay, so we're going to talk about quite a few topics here, starting from like how the enums, structs, vectors, strings are laid out in memory. Going to look at pattern matching, what's really going on, and how good it is. Like how if you compare pattern matching to what somebody would write with if statements, how close does it get? And how are smart pointers managed in memory? Then we'll look at tail call optimization when it happens and when it doesn't happen. And basically Rust is kind of a best effort tail call optimization. So if the last function would get optimized, but there's no guarantee that it will happen. And we'll talk about what tail call optimization is. We look at dynamic dispatch and vtables. Rust does dynamic dispatch differently from C++. And so we'll look at that. Then we always hear that functional programming in Rust is a zero cost abstraction. We'll see an example of that. Then We look at what closures are and how they capture the environment. And finally, we look at async await from 2 points of view, like from the function's point of view, and from what an async executor, what does it look like to an async executor? Stuff frozen. So this whole presentation is more like few examples, and we'll look at either the assembly or a low-level details of what's going on in the system. Let's start with an enum. Here's an example of an enum with 3 entries, and the way it's laid out in memory is shown in the table below. It's basically a union, and there's a discriminator field that gets added, and it's a 64-bit field that's getting added here, but the compiler does optimize it based on if it can find a padding, or in fact, it actually can be opportunistic and completely remove it if it's able to infer by looking at some other field if there is a difference between the two. And like, for example, if some field is 0, it's going to be 0 in some case, it's actually going to hang on to that and use that to determine, use it as a discriminator. So in this particular example, it actually just puts in an 8-byte field, a 64-bit field, and depending on what the discriminator's value is, the compiler will either put an I64, F64, or 2 F64s as required by this code. And now let's also look at an example of simple pattern matching happening to, let's say, double some number. Again, this is not a mathematical double, just adding stuff up to be, and you can see it's performing the same operation on an integer, floating point number, and a complex number. If we go under the hood, what's really happening is you can see here that the compiler gets in, looks at the discriminator, and performs all these operations that are needed and returns. You can see that for 64, for complex numbers, it's actually performing, it actually automatically starts using vector operations and performs the real and the imaginary part are computed together, addition, multiplication, everything happens in short. The main thing is here is that the discriminator, which is completely hidden from the developer, is added by the compiler, and it uses it to perform the different legs of the code. And Rust performs this in a very type-safe fashion. So there is no way to, unlike C, you cannot go and wrongly interpret a union. This is, I think, the way I drew it in plant UML. I think so. It actually just does a single if. I think so. Okay, so let's look at box and arc and what really happens along with the computation when we are dealing with this. These are like simple examples which are probably not practical, but like, for example, if you're passing self as a box or arc as a box. So we'll look at these two cases. So if we are passing self as a box, the compiler will perform all the operations required by the code. And after that, since the box is going out of scope, because here we took ownership of the box. So as you can see, we didn't pass a reference, we are passing the box itself. The compiler will call the Rust deallocate function, which we actually normally don't deal with ourselves. So it calls the Rust dealloc, which will free the memory. And so this is, again, something that you don't see, but it's actually going on behind the scene. And if you look at for an arc, if you're taking ownership of an arc, same thing happens. In this case, the compiler just inverted the action. So it looks at the reference counting. It looks at the what's called a strong. It looks at a strong and a weak reference. And if they are both going to 0 after this function, it's going to drop the memory, and then it performs the computation. In this particular case, before dropping the memory, it actually copied the variables into register, so it just performed in them in a different order than what you would normally expect. Okay, now let's look at another curious thing. Structs in Rust do not guarantee the byte order by default. In fact, actually, they do something which is somewhat clever in the sense they'll Rust will reorganize your structs to minimize padding. So it generally tends to put the larger fields up and the fields that require smaller alignment later. This minimizes padding, but there's no guarantee of any order. So you should not assume that the fields are going to be in any order. And you can see if you're interoperating with C or you want some order, all you have to do is say REPR C, and then the compiler will maintain the order, and this would work with a C compiler. So if you send a struct from Rust, it will be received in C and vice versa. So this is another small thing in Rust which makes Rust beginner friendly. If you're a new person to programming and you don't understand the ins and outs of padding, the compiler is taking care of this kind of stuff for you. So it's just reordering fields, and if you added, let's say if I added a U128 field, it would have put that right as the first field. Okay, and now let's look at arrays. Arrays are actually just a stream of bytes, nothing different from any other programming language. Array slices, when you use an ampersand, are basically they contain the address, the starting address, and the length of the array slice. So array slice is kind of a window into an array. So both are not super exciting from the point of a memory layout, but that's what they have. Now let's also look at the computation involved in pattern matching for an for an array slice. So here we are looking at a field A that we want to extract from these different patterns, and if it doesn't match these patterns, we want to store as 0. So the way the generated code from Rust is actually pretty similar to what you would actually go and write. What it does is, again, I've added a copy of the code here. So first thing it does is compares with the length with 4, which is for matching this pattern. And then it goes on and performs these checks for 45, 46, 47, and finally extracts data 3, and that will be returned to the user. And similarly, once it's done with this, if the length is not 4, then it's going to perform a check for length 3 and perform similar operations and return data 2 or data 1, as the case may be. Okay. So again, see, you can imagine, like, if you were writing the similar code in C, you would have to deal with this complexity of having so many if statements. Here, it's easier to read, and once you get used to pattern matching and the match statement, you can see how much of code is being saved by not having to deal with all this stuff. And it's so error prone to write if statements like this. Okay, so if you look at a vector in Rust, if you look at the declaration in the compiler, it's slightly wonky, and because it uses a marker type and places fields slightly differently than what you would expect. But in reality, what we really have is we have a pointer to a buffer, which is actually a heap allocation, then a capacity. In this case, like, the capacity would be eight entries, and the length, which is how many entries do we have currently. So the compiler would, the library would go and keep adding entries here, and if it runs out of space here, then it's going to allocate a bigger buffer and start sticking in entries, and in that case, it will also copy all these entries over. Okay, the important thing to remember here is this is a heap allocation. So whenever we declare vectors, we are actually causing a heap allocation. Okay, strings are really no different from a vector. So they are really vectors which contain UTF-8. So again, it's the same structure. So when you pass a string, you're actually passing this part, and it points to this heap memory allocation here. String slices are similar to an array slice. Again, they give you an immutable view into a string from a starting point to a total number of entries. So in this case, it's just pointing, let's say, into this string, but you just look at hello here. Okay, so now let's look at functional programming in Rust. Is it really a zero cost abstraction? We can't say that by looking at, I'm just looking at one example, but from my experience, what I saw is the compiler does optimize everything away, like unlike many other languages where you do have cost of sometimes getting into function calls. Rust seems to be eliminating function calls in most cases. Again, this is a contrived example where you are calling a fold operation, which is actually just collapsing these entries, and you can think of this as an accumulator being added. There's an initial value, and then you're performing a function on each entry and collapsing all of those entries into a single result that is being returned to the user. So in this example, I've taken the fold is basically what we're doing here is we are actually taking we have an array which contains 3 functions, and we want to see we want to apply each of them, and the result of the total fold operation is going to be the addition of all the results from each and every one of those functions, I think. So in this example, I have 3 functions, and basically what I'm doing is I'm saying multiply by 2, add 1, and multiply by 2. What the compiler does in this case is it inlines these 3 functions because they are small, and it also collapses them together. So if you look at it, you can think of these as polynomials, and so finally we end up with a polynomial 4x plus 2 by combining all these 3 operations. So, and what the code you get here is looks something like this. We're zooming out in this area. So there is a vector of 1024. We are looping through 1024 entries. What the compiler does is in each iteration is it's able to compute 32 of those entries. Again, this was with 16-bit integers. So you can see it's performing 8 multiplications and 8 additions in parallel, and then it does that 2 times. So what you end up with 32 operations getting performed in a single loop iteration, and there are 32 such iterations to take care of 1024 operations. And this just shows that I think we have a lot of CPU power left on our computers which we don't use fully. In this case, and this might be a case where you actually use it more than what you would in reality, because here the compiler knows in advance what the length of the array is. If it doesn't know the length of the array, I haven't included that example here, but what it does is it generates code for if it's a multiple of, let's say, 8, then use this routine, and if it's a smaller number, let's say 4 entries, it will generate some code, and it actually weaves them together to handle all entries. So if we can tell the compiler the total number of entries, you get more efficient code, but you still don't sacrifice on efficiency because the compiler does do length checks, and based on that invokes different parts of the code to cover all the cases. And it will actually use them together, right? It will cascade them. If you have a multiple of 8, then 2, so it will put 2 or 3 things together to compute the full result. Okay, one thing I didn't cover earlier when in that function was the function is returning a vector, which means right off the bat the compiler is going to allocate memory. Since this was a U16, so it allocates 2048 bytes for a 1048 byte array, and it sets the alignment to 2. So whenever Rust allocates, you have to specify both the values, the size and the alignment of memory. Okay, so here, one thing to keep in mind is that when you're calling a vector, you are you can see a panic if you run out of memory. So, which is actually not a big deal, because in any other programming language, if you run out of memory, there's very little you can do in your application. It's going to die anyway. So as long as we just need to know that most likely the application is dead when you are out of memory, but this is what the compiler does, generate this code for panicking in this case. Okay. Any questions up to this point, or I can keep going? Okay, so let's look at traits, vtables, and tail calls. Okay. Here I've shown some traits. You can see a shape trait with an area function, where it actually, the way the code works is the user doesn't have to actually, the code you're writing may not have to know about the actual type of the field we are dealing with, or the type we are dealing with. Similarly, here it's here's a draw trait, which actually kind of extends the shape trait and adds another method. So we'll look at the code generated for these cases. So as you can see, the compiler does not know the actual type, because we are using the din keyword here. So it'll have to call the draw and area functions through an indirection. Okay, so before we go further, let's look at how Rust performs dynamic dispatch, where you actually don't know the type of the operation of the concrete data type. So the way it works is, it has a pointer to the concrete data type, and it keeps a vtable pointer, in fact. So these are called fat pointers in Rust. So you have basically two 64-bit numbers sandwiched together. So it's kind of, you can think of this like a tuple. And this tuple carries this vtable pointer, which contains a destructor, which I haven't seen getting used too much, but it's there. And more importantly, it contains pointers to the methods of the concrete type, which the caller of this code may not know about. Okay, so like, for example, method 1, method 2 here. And it also contains size and alignment for the data structure. This is needed. Imagine if we were dropping a box containing like a din pointer, we still need to free the memory. And so you need to know the size information in the vtable. Okay. So let's look at like this draw dynamic function, where you get a din pointer to a draw din reference. So in this case, one would expect that there will be a function call in assembly, but what we actually see is a tail call, which is meaning that the compiler actually just performs a jump to the code instead of creating a stack frame. It's able to get away with this because effectively what we are really doing is we are fooling the called function into thinking that we have arranged a stack frame, and when the function actually returns, it's not returning to the caller, but it is returning to the caller of the caller. So here it shows what really is happening. The caller calls draw dynamic through a vtable entry, and at this point the compiler sees that the stack is already prepared for this function to even return. Everything that we want at the end is already set up, and the result of this call is going to be returned anyway. So we trick this function into thinking that it is returning back to draw dynamic, though when it returns, it actually returns back to the caller itself directly. So that's why if it was a call, then a stack frame would have been added for the return address of draw dynamic. But since we are just jumping to it, the stack just contains the return address of the caller, which is this function. And when it returns directly to this function. So we are saving stack frames and allocations for this call. So you can say that Rust is not able to obviously inline a dynamic dispatch, but this is the next best thing it can do. It's able to reduce some overhead here. Okay. what happens if, let's say, we had two calls? We had a call to draw and area. So quite predictably, the first call cannot be tail call optimized, and it has to be made as a conventional function call. The last call here is the compiler is able to tail call optimize it, just the same way as we saw in the previous example. Okay, let's look at another aspect of tail calls. So consider this binary sum operation where we're dealing with a recursive call where there's a left call and a right call. And you can almost predict that the compiler will be able to tail call optimize this part of this call, but it will not be able to do so here. So what the code generated is something like this. So if it's a leaf, it is just going to it generates a sum function. If it's a leaf, it just returns immediately. If it is not a leaf and a node, you can see the curious mix of recursion and iteration happening. So we are recursive on the left side, but we are iterating on the right side. So the way the full function executes is we for all these calls, we are going with recursion, but we are performing for loop operations for this side of this. This is actually no different from what we saw earlier, where there were two calls. The first call could not be tail call optimized, which would be this call. So recursion lives here. In the second call, you can think of it this way: the function, the code is kind of getting tail call optimized, but then the compiler says, wait a minute, it's the same function that's getting called, so it's able to convert this into a for loop. So, okay. Okay, closures. This is again a very simple example of a closure. What we are doing is here we are retraining a quadratic function, which is a custom function we are forming with A, B, and C. The code generated here is actually just to copy so effectively what preparing a closure does is it just prepares a struct, which is hidden to the user, which contains the fields that you specified to be captured here. So the return from this function, you can see it's just copying A, B, and C, and are being stored into a struct, and it's being returned. So the compiler knows that this is a closure, so it knows that these are the captured values that have to be used. Okay. Okay, fine. We are on the final subject here, which is async await. We're going to look at what happens in an async function. Here, it's like in a video game, you might see a patrol function where you have a sentry moving between two entries, moving, let's say, from one position going to another position. And so it awaits reaching this position. And once it reaches this position, it awaits reaching position 1. So what happens here is the compiler actually converts this function into a full-fledged state machine. So it starts with, in fact, it adds a state variable just like we saw a discriminator. In this case, the compiler will add a state variable into the function to identify what are called the await points, because these functions are resumable. So whether we are at this point, or we are awaiting something here, or we are awaiting here, all these would be captured in a single state variable, which is shown here as 0, 3, and 4 values. So when you invoke the function, it'll call the poses 0 await. So it's in a state waiting for the result to reach this value, and when we return ready from here, it's actually going to transition into this state and start waiting for this procedure to be for poses 1 await to be finished, meaning that the sentry reaching the position 1. And once it is done, it'll go back to state 0. So you can see here that this is actually an infinite loop, And the infinite loop manifests itself as a state machine cycle here. So you transition the states this way, and we'll see in future slides that this is somewhat counterintuitive. It's an infinite loop, but the function returns periodically. Whenever we have to await something, the function will still return. Okay, so this is how the code really looks like. And I'll look at I'll show the 3 different pieces of it. So when you start into, so you are at this point, okay? You start here, you make your function call. If the closure is going to return ready, means that whatever await condition was there, if it is satisfied, it can go and call the next condition, which is looking for position 1. And if this function is again has reached that position, it's going to return here, and it'll go back to the start state again, because this is like this code executing. And if effectively what's happening here is these function calls are being replaced by poll calls, which I'm not covering that. We'll look at that a little bit later, where the polls actually return ready, or they return await or pending. So if it returns pending, we wait in this state. If it returns ready, we move on to the next state. So that's what's happening in these cases. So this is a state where you started. So you can very quickly go back to the state if, let's say, the results are available all the time. Otherwise, you will block. Like, for example, here, if the result is not available, you're not going to block in the conventional sense of the word, but more like the function is actually going to return back to an executor. We'll look at that. And it will be executor's job to call the function again, but the function won't start from here. It'll remember the state, and it'll start from this point. So we can see here, if we had blocked awaiting a result from here, the function resumes at this point and performs the closure, goes into and it reports. If it again gets a result ready, it goes through the next closure. Again, state machine transition happens same way. Okay, and again, if it is polling on the second position, it will wait until the final result is. And finally, you can see that if we are awaiting a result here and we get a result, which is poll ready, we're going to go back to the beginning of the loop. Okay, otherwise we'll return. These are actually, whenever we say poll pending, this is actually a return call, and we'll see that in the next slide. Okay, so here is, we are looking at the same async function, but from the point of view of an executor. The executor is actually running the whole state machine. It's keeping track of how the async operations are. So what it's really doing is it's basically making poll calls. It's making a poll call with the environment context, and the function starts in this state. And this is basically our first call happening here. Go to and await. So from the executor's point of view, this looks like a function call where it calls poll. If poll returns ready, it's going to go and perform okay, in this particular example, I've just taken an example here. So here we are moving to that position. So if this poll returns pending, somebody has to go and reschedule this operation for it to make progress. In this particular very simple executor, it actually keeps polling repeatedly. So it returns, then the poll call is made again, and eventually when the scheduler reaches, when this closure reaches this point, or the go-to closure, it's going to return a poll ready here, and then it will call future operations here. One thing to note here is our infinite loop is in this patrol closure. You can see that it never returns back to the scheduler when ready. because that's the nature of the infinite loop. This whole function is an infinite loop, but it's returning whenever there's a poll pending. So in async world, you can think of infinite loops as functions that will actually never return poll pending. They'll keep returning ready here, and it's just going to return pending. So this shows another call being made here, and so this is this code returns here. Finally, we reach this state where we are awaiting the result, and we keep returning pending. And this way we enter when the disclosure returns the next time, we are back in the start of the function, which is this point. Okay. I think I've gone maybe too fast from the presentation. Yeah. So we covered these areas. So if you guys have any questions. I used Godbolt. Yeah. What was used for doing the disassembly of the code? It was all done using the compiler explorer or Godbolt, and it's pretty nice. The only thing is it doesn't support ARM. It supports x86, 64, and you can actually do quite a bit of things. You can even compare two functions and do all kinds of operations. And in the book, actually, I put in links to the Godboard pages. You can actually get tiny URLs, and anybody can go and visit them. And like I've added examples also, you can modify things and see what happens. It's kind of fun to see if the array was, let's say, 1024 entries, you go and increase it to 5 million entries, what does the compiler do? And at different lengths, sizes, the code generated might be completely different. So if, let's say, the array index was 32, the compiler will not generate the for loop at all. It will just inline everything. So it's interesting to see. I think I would say optimizers are the unsung heroes, which we don't talk about, but they do amazing amount of work, I think so. Yeah.
Strings. Can't you also get the link? So, but this number of bytes might be different from the string.
Yes.
Some
Yeah.
characters require more than one byte.
Right.
How is that handled?
I think yes. So the length of the string is actually not okay. So the question is actually, I'm probably not well equipped to answer this question, but in different languages, like for example, the length of the string might depend on what that string is in that particular language. And in Rust, the length I'm talking about is the UTF-8 length, which is like for each of these bytes. Maybe Sagar, you spent time on this? I think so.
So anything else is, but graphenes is really, I tried to bring it.
If I ask for the length string, I'm getting the number of bytes. I want
It
to
might be-
really know how many characters.
Yeah, in Rust, what you get, the 3 words are the pointer. It's the number of bytes that are in the string right now. The third one, and this is also true of vectors, is the capacity.
Yeah.
So how much currently allocated memory there is. So those are the 3 words, right? Whether it's a 64-bit OS, it'll be 64 bits.
Yeah.
And so when you're asking for length in Rust, you are not getting the graphemes. You are getting the bytes. That's what you need. If you do want to get the graphemes, there's an excellent crate. I could not begin to pronounce his last name, but I will try. Manish Gregor. But he did a really good library that actually handles strings correctly. And so you don't have to do this yourself. This is for accounting characters versus bytes.
It's actually, yeah, yeah. Okay, any other questions, anybody? Yeah.
I'm asking as a non-professional programmer, or of a hobbyist programmer who does not have a comp sci degree. But I'm very, so nuke me here on this beginner question. But what types of programming are you doing professionally where you're spending a lot of time worrying about the memory layout of a program? Because I'll write scripts, I'll write dumb little games in Rust and stuff like this, like handy little string manipulation tools, and I've never once worried about memory layout. So for someone who has no comp sci degree and is not like paid to program, what can you tell me about who's worrying about memory layout?
Yeah. Okay, I would say that's actually a great thing that with Rust you don't have to worry about memory layout and all this stuff. Oh, sorry. The question is, like in most use cases, you don't have to worry about memory allocation. What are the use cases where you do actually have to look at memory allocation? In Rust, typically, that's actually a great thing that you don't have to worry about it. Like one example I ran into was, and in fact, that's a Clippy warning, that if you're using enums and you have, like as we looked at it, okay, the enums are union structures, okay, so if you stick in one of the enum entries is like greater than 256 bytes, it starts warning that maybe you need to rethink this. You might have caused this whole thing to blow up to a much bigger size. So there are sometimes that you might have to worry about. Other applications which I actually am personally struggling with is like when we move to Rust, not everybody is going to move with you. Okay, so I'm working on a project where some part of the code is in Rust, and most of the project is not in Rust. So what happens is we have to figure out how to exchange information with, let's say, the C code or Rust or C++ code. So you have to format into that structure. But yes, most of the time you should not have to deal with worry about these memory allocations. There are some cases where it does become a factor. Like for example, we looked at closures. Okay, so if you go very deep in closures and have lots of awaits, you may end up with a very big struct that gets created internally.
Thank you.
Oh yes, yeah.
Especially in the case of large struct heading. Common game data structure. Yeah. If you're using that, you want your objects to fit cache. Because that's the closest thing to your die, and you want that to be as fast as possible. So yeah, that matters. If you're sending stuff to the GPU, you care about memory layout.
Yeah.
If you're running database stuff, you definitely care about memory layout. So there are a few cases, but they're more hardcore than it sounds like you're talking about this point. I'm very much just
Yeah, for those online, there was an answer that said games are also very important in this space where you care about your your memory layout, because for your objects it has to fit into the cache on the CPU. If you're dealing with GPUs, you care about your memory layout. These are also very important.
Yeah. One example I can go ahead.
You have an enum that represents like display, position, absolute, relative, whatever, I don't know. You only really need 4 bits to represent that. If you're doing padding, you're wasting a lot of space. And you're copying around these big objects, even though you have to need to. And web browsers just creating loads of these things because JavaScript is terrible language.
That's why I've never explored like development.
Yeah, one more case which actually I have not covered is that in Rust, array indexing is always bound checked. So if you are a C++ developer and you want to prove that Rust is slow, easiest thing to do would be just show a matrix multiplication application, and obviously there'll be bound checking. The compiler does eliminate them, but it will not completely eliminate them. So that's why when you're using matrix multiplication, you're going to use some other crate in Rust rather than just rolling your own matrix multiplication program.
Would it matter more in embedded applications than maybe like on OS?
Okay, so the question is, will it matter more on embedded? Sure, I think we have an expert here on embedded. Like there is something called no STD, where you have to worry a lot about different sizes. Yeah. Okay.
Yeah.
In my car project, I'm sampling data. If I used a CAN bus, a car area network bus, the high speed, get this, high speed CAN bus is 1 megabit. So we think about, what's the slowest USB standard? USB 1, and wasn't that like 12 megabits, right? So no one would ever use USB 1. So we're in a completely different realm when you're dealing with embedded systems. You're dealing with kilobytes or less of memory, right? Hundreds of kilobytes or less. So in those cases, you care very much about padding as well. It's another good example.
Thank you,
Okay.
You're welcome.
everybody.
Okay.
Great.
Thank you.
Oh, there's a question in the back too.
Can just exit it now. I can exit.
And on how you, like, you have like an followed by array of that length, things like that. And getting that, get it wrong, and you'll have a bunch of. And then.
A grossly oversimplified summary of that for the online viewers to say it also caring about your sizes, how your data structures are packed matters if you're designing language, writing data structures, and creating a compiler. Great. Okay, well, thank you very much, Sandeep. A round of applause, please. Okay, so if I hurry, we should have just enough time to run this little experiment. So, I'm not me. I am, of course, there's no power coming out of that plug. Okay. I'm not me. I am me of 10 years ago, learning Rust. And I'm here as a beginner, trying to understand this crazy concept known as Rust lifetimes. How many here are currently struggling with lifetimes? Anyone? Right. Now, exactly, always is a very, very good answer. I've been using Rust since 2015, and I don't consider myself a lifetime expert. And so every so often, I still get myself into trouble with lifetimes. So if you're beginning with Rust, and you're like, what the heck is this tick A stuff? And how does that even supposed to work? I don't particularly like the way it was explained in the Rust book. I actually had an opportunity to collaborate with Steve Klabnik way back in the early days to write the Rust book. And I had a lot of questions for him about why it was written the way it was, because I just looked at the world differently. And I think he quickly realized that, nope, I don't want to work with this guy. I want to work with somebody who's, going to help me get this done, not sort of try to start things over. But it really was difficult for me to pick up Rust initially from the Rust book. And what really helped me was the programming Rust book by, I'm going to forget his name now, but it was a programming Rust book. And the author approached it from, I think, an approach that was much more familiar to me as a systems programmer. And I'm going to remember his name just before it shows up, but Jim Blandy is the primary author here. And so if you're coming from a systems development background, that's at least the book that certainly helped me a lot. Even things like operator precedence, things like that. Some of the things that Sandeep was talking about what's really happening under the hood. The current Rust book doesn't approach it that way. Steve Klabnik comes from a Ruby background, and so he's not coming at it from a systems development background. And now in hindsight, I can see this is why it was harder for me to grasp, how he was teaching. So I would like to share this video with you. I thought it was really interesting. Hopefully we'll learn from it. And I would just like to lead a conversation using this video with I think an excellent video provided here to us by Ledoux. I don't know his real name. Let me see if this audio is going to work okay.
Like pretty much everyone else, in the beginning, I struggled quite a bit. Where I was fairly comfortable using lifetimes. But they all into how the borrow checker worked internally.
Wow, I never would have figured that out. Thank you.
Let's talk about lifetimes. This graph shows my understanding of lifetimes over time. Like pretty much everyone else, in the beginning, I struggled quite a bit. Eventually, though, I reached a level where I was fairly comfortable using lifetimes. But they always remained somewhat mysterious to me. I never really had a solid mental model that allowed me to think of them and write code without needing help from the compiler. But all that changed when I started looking into how the borrow checker worked internally, because I learned that there are actually two different ways you can think about lifetimes. A bit like how you can think of an electron as both a particle and a wave. And sticking with this analogy from physics, the problem is that the official Rust learning resources only tell you about the particle interpretation, leaving out half the picture. So my goal in this video is to introduce you to the world of lifetime waves. Well, okay, this analogy is kind of falling apart. In any case, I want to introduce you to this other way of thinking that I personally find much more intuitive. But we'll start with a classic interpretation and an example from the Rust book.
Okay, so as a beginner, what he's saying to me is starting to resonate, right? I heard some concepts. I feel I didn't get the whole picture. I read up on the book and I went off to try to do something and I got smacked down hard. So I'm like, okay, I got this. Hopefully he's going to help me out here.
You may have seen this code before. We create a reference to the variable x in an inner scope, store that reference in the variable r, and try to use that in the outer scope to print the value of x. This, of course, is not valid code, and the bar checker will happily complain that x does not live long enough. So far, so good. The Rust book then goes on and tries to explain this error using the lifetimes of the variables x and r. The idea is that r clearly lives longer than x, and because r points to x, this is invalid code. There's just one problem with this explanation. If we remove the call to print, this code is now valid, even though r still points to x in the outer scope. However, because r is not actually used there, this is not an issue. The problem is, if we look at the lifetimes of the variables again, these haven't actually changed. R still lives longer than x, so what's wrong? Well, what's shown here aren't actually lifetimes. These are scopes, parts of the code where certain variables can be accessed. A lifetime is something else. The Rustonomicon defines them as named regions of code that a reference must be valid for. Okay, let's unpack that. These scopes are indeed named regions of code. That part is fine. However, they don't specify where references must be valid. First of all, x is not a reference at all, therefore it doesn't have a lifetime. And second, even though r is a reference, the region of code ticr does not actually specify where the reference r must be valid. Intuitively, that wouldn't make any sense, because up here, r isn't even initialized, so r's lifetime cannot start before this assignment down here. And then after the print, we don't actually need r to be valid anymore, because it's not used there. So in fact, this is what r's lifetime actually looks like. But
any questions with that? Does that make sense to folks? Right? It's like, yeah, see? Right? That's kind of how I was feeling when I was listening to this.
If there's only one lifetime in this example, then why is there an error at all? Well, that's because r's lifetime crosses the closing curly brace of the inner block, where x goes out of scope. And because r points to x, that is not allowed. If we now remove the print again, then r's lifetime collapses, because r isn't used anymore. And because its lifetime now no longer crosses the closing curly brace, this code is now valid. Alright, now we have a rough understanding of what lifetimes are. They're regions of code that certain references must be valid for. Makes sense, right? Well, let's say we come across a struct definition that uses 2 lifetimes. This is a bit weird, isn't it? We're looking at a definition of a data structure, but it uses lifetimes, which are regions of code. So if we want to understand what this definition actually means, do we now have to think about regions of code? Well, to me that never made too much sense. And we'll get to how I think of definitions like this now, later on in the video. First, let's have a look at another example, which we'll use to introduce this other way of thinking about lifetimes. This example is similar to the previous one. Again, we create a reference to x in the inner scope and assign that to r. Only this time we print the value inside the inner scope. Then afterwards, in the outer scope, we reassign r to point to foo, which is declared at the start of the function. And again, we print what r points to at the end. However, this time the code is valid, even though r is the reference in the outer scope, and that's of course because it was reassigned to point to foo before the read. Now let's have a look at the lifetimes again. Here we can see that r's lifetime is now split. And that's because lifetimes are computed using a concept known as liveness. Liveness is fairly simple. A variable is live if its current value may be used later in the program. So going back to the example, we can see that this use of r in the inner scope is the last use of r before the reassignment in the outer scope. Meaning on these 2 lines in between, r is not actually live, which is why its lifetime has a hole here. But this picture is actually not complete, because we don't just need to know where r needs to be valid, we also need to know what r can point to. And we've actually used this information implicitly before. Let's remove the reassignment of r. Now we have something resembling the first example. And if you recall, we said that this was invalid because r's lifetime crossed the closing curly brace where x went out of scope. But that's of course only an issue because r points to x. If it pointed to foo instead, this code would just be valid. But let's undo all of those changes. Instead, let's make the reassignment of r conditional. Now the lifetime of r is no longer split, because if the branch was not executed, r still points to x. But if it was executed, r now points to foo. And the fact that r may point to either x or foo is represented by this set notation over here.
Any thoughts on where we're, like, what's the borrow checker think about this? I see smiles. It can't be valid, right? So the borrow checker is always going to be conservative, right? If it's possible to do the wrong thing, then that's enough to invalidate the code.
So now you can see references actually have two properties we care about. The first is when they must be valid, as in which regions of the code, and second, what they can point to. And this second property, what a reference can point to, is what we'll explore in the rest of this video. You see, a reference really is just a special kind of pointer. Special because it has this take A thing that the compiler uses to validate that the reference never points to invalid memory. And usually we think of take A as the reference's lifetime, as in which regions of the code the reference needs to be valid in. But as we've just seen, that's only half of the equation. So what if instead of thinking about take A as when the reference needs to be valid, we thought of it as what the reference can point to, as in which region of memory? Let's illustrate this idea with an example. Here's the function longest, which just returns the longest one of two strings. Now let's think of this take A as some region of memory. Note that it doesn't necessarily have to be contiguous. What this function signature is saying is that the function takes two strings that both live somewhere in this region of memory take A, and the function returns some reference into the same region. While this example is fairly simple, just being able to visualize lifetimes using a familiar concept, namely memory, without having to think about code or time, is why the region model is so useful to me. Now let's see what using this function looks like. Here we have three variables x, y, and z, pointing to the strings hi, hello, and hey. Below, we compute the longest one of those strings. Now, all of these variables are references, so they all have a region, or lifetime. Next, let's visualize these regions. So x, y, and z each have their own independent region containing their string. Let's ignore the rest of memory and focus only on these regions. Okay, now let's figure out what take L1 is. The variable L1 is initialized with the result of a call to longest with x and y. Looking at the definition of longest, it may at first seem like all references involved need to have the same region, because in the signature they all use take A. And this would mean that we'd have to unify the regions of memory take x and take y, making them no longer independent. However, if it worked this way, references would be really annoying to use. Because if you think about tick x and tick y as lifetimes for a moment, this would mean that the strings hi and hello would have to have the same lifetime. In this case, since we're using string literals here, which all have the static lifetime, that would be fine. But let's say hello was allocated on the heap instead. And we simply wouldn't be able to call longest with x and y, because their values have different lifetimes. The string literal lives for tick static, but the own string only lives until the end of the scope. And this problem is what subtyping and variants are about. But that's a topic for another video. For now, all you need to know is that this call to longest actually creates a new region tick A, and in this case, that needs to be the smallest region, such that both inputs of the function are contained within it. So in this case, tick A includes tick x and tick y. Now, since the result is assigned to L1, let's call this resulting region tick L1. And similarly for the second call, a new region is created. This time it must include the new tick L1 and tick z. And let's call this one tick L2. So this is what the lifetimes in this example look like when interpreting them as regions of memory. Alright, next let's talk about outlives. Interpreting them as...
Does this make sense? Okay. It's a different way of thinking about lifetimes that I've heard, than what I've heard before. And I think it's a lot more intuitive. So if this makes sense, maybe this will help.
Regions of memory. Alright, next let's talk about outlives, what it means and how you can think about it. In Rust, we can require one lifetime to outlive another one. It's not super common that you have to use this feature explicitly, like in this example, but implicitly you do actually use it pretty much all the time, perhaps without even realizing. In the last section, we talked about how, at first, the signature of the function longest seemed as though all references involved had to have the exact same lifetime. And we talked about how, if it worked this way, that would be pretty annoying. But for the next example, let's pretend this was actually how lifetimes worked. Two references using the same lifetime parameter need to have the exact same lifetime. And our goal is now to change the function longest to still allow the user to pass in strings with different lifetimes. To achieve this, we have to use multiple lifetime parameters, one for each input and one for the output. However, making this change breaks the code, because the references we're trying to return are now unrelated to the output lifetime. But we can fix this by adding outlives constraints. The question is just, which ones do we need? While the compiler error you'd get for this code would actually just tell you which ones you need, we're of course trying to understand lifetimes and arrive at the solution ourselves. And to do that, we need to understand what outlives actually means. And to do that, let's switch back to thinking about lifetimes as regions of memory. So here we have our input and output regions. Currently they're unrelated. What we now have to tell the compiler is that both input regions need to be contained in the output region, so that we can return either of the input references. Now if we think of these regions as sets, that means we need two constraints. Tick S1 is a subset of tick out, and tick S2 is also a subset of tick out. Just simple set theory. Now, it just so happens that the outlives constraint in the region-based model is actually just a subset constraint. That's what it means. So these two constraints here are exactly what we need in the where clause to make our code compile. So in summary, if you come across an outlives constraint, you can just think of that as a subset constraint. In my mind, I read constraints like this as tick A in tick B. And you can of course also think in terms of lifetimes and which of them need to outlive other ones, but to me at least, the regions and subsets are a more direct way of thinking about references. Oh, and the reason I said you're actually using outlives pretty much all the time implicitly is because the longest function, as is written here, is basically how the longest function with a single lifetime works under the hood in real Rust, thanks to subtyping and variants. Alright, we have two more things to cover, but I'll keep those fairly short. So, what do lifetime parameters and structs mean? Well, we can just think of those as regions of memory that references in the struct can point into. So that's not too advanced. What's more interesting are the kinds of errors you can run into when using lifetimes and structs, and how to avoid those by using multiple lifetimes. And I'll talk more about that in the next video about borrow checking. But don't expect that too soon. And the last thing is tick static, the static lifetime, which you can kind of think of as the data section of your executable. Although that's not fully accurate because it also includes leaked allocations. But that's going to be it for this video. Hope you learned something, and if you did, do let me know down in the comments. I'd be curious whether this idea resonates with anyone. Oh, and I've also linked the article that originally inspired this video down in the description. If you read it, you may notice that they actually define lifetimes as sets of borrows, not regions of memory. But in my opinion, regions of memory are easier to think about, and a good enough approximation in most cases. Alright, that's it.
Right. Thank you. Thank you. I tried hard. I tried hard. What do you guys think about that? Yeah, it was helpful. I have read the article. I had actually previously read the article that he's referencing. It's a Nico Matsaki's article, one of the leaders of Rust. And I did not extract what he was able to extract from that article at all. What he pulled out of it really clarified a lot of things. So I hope that was useful. There is a link to this video in the slide deck. If you click the video, you'll get right to this video. If you click the link in the slide deck, you'll get right to this video, so you can watch it again, or if you have questions, feel free to hit me up on Discord and we can chat about it. All right. So yes, there's a get-together today at Flatstick Pub, so as always, so if you want to join afterwards, please go ahead. As I mentioned earlier, I won't be able to join tonight, but I look forward to doing that next time. Okay, thanks everyone.